So now we're going to move into chapter 3, and we're going to start out with quadratic functions and some models that relate to them. So before we can specify what a quadratic function is, we've got to talk about the more general term. So I've said the word polynomial. You've probably used them before in college algebra as well. But specifically, a polynomial function, which we'll call f, of degree n, where n is a non-negative integer, so it's important that it has to be an integer, is given by a function of this form. So you have some constant, an, times x to the nth power. Another constant could be the same as the previous one, might not be. And then you get the next power down, so this is also going to be an integer. And you keep going through, you have another constant times x to the first power, another constant, and you can kind of think of it as an x to the 0 power here. All of these coefficients out front are going to be complex numbers. More often than not, we're just going to deal with real, but in a general sense, a polynomial has complex numbers as the coefficients. And the one thing that cannot be 0 is this first coefficient. So an, the one attached to the nth degree, cannot be 0. Otherwise, it's not the full degree. It would be an n minus 1 degree polynomial. So you want that first term to have a non-zero coefficient, that highest power. So now a quadratic function is this very specific type of polynomial. So all it is quadratic, it's second degree. So it's a lot like solving those quadratic equations we have. We have our function is equal to ax squared plus bx plus c. And again, these coefficients that are out front, a, b, and c, are complex numbers, and that one attached to the x squared cannot be 0. But b and c, perfectly fine if those are equal to 0. Okay? So we have a couple different forms. This specific form where it's just all expanded out, you have a, b, and c, that's general form. Standard form is a very specific way where you're going to have that coefficient a times x minus h quantity squared plus k. So you see it's kind of like that parabola, but it's been shifted left and right, and it could have a reflection depending on the value of a, or a stretch, or a compression. But the reason we like this standard form is it's going to be super helpful for us for graphing. So one of the main reasons is that point hk is going to be our vertex. So it has the same shape as that parabola, but now when it's in this standard form, you can see where that vertex is going to be moved. Also, based on the value of a, we know the orientation. Is it going to open up or open down? So if you think of y equals x squared, that opens upwards. So if the value of a is positive, we know the parabola will open upwards. If the value of a is negative, then it's going to be opening downward. And then also, this parabola's and quadratic function is symmetric about that vertex. So also, x equals h, which is that x coordinate of the vertex, is our axis of symmetry. So basically, the parabola can be reflected across that axis, and you get exactly the same thing. So let's look at two graphs based on those values of a. They're going to be very similar to each other, but have slight differences. So our vertex is somewhere in the xy plane. So here's x, here's y, here's x, here's y. So our vertex could be anywhere. Let's make it in the first quadrant. Here's h, here's k. So here's our vertex, hk. And for the second picture, let's put it over here. Here's the x coordinate, the y coordinate. Here is hk. So then our axis of symmetry in each of these cases is a vertical line x equals h. Same thing over here. Here is our axis of symmetry, x equals h. So in both of these, the green line is our axis of symmetry. Okay. Now our parabola, in the case when a is greater than 0, opens upwards. So it opens up, and then you reflect it across that green axis, and you're going to get exactly the same shape. When a is negative, that just tells us it's going to open downward. And then again, you reflect it across and you get the same shape on the other side. So these are what our parabolas will look like based on the value of a, and then based on where that vertex gets shifted to. So let's go ahead and let's graph a function, a quadratic function, which is going to be x minus 4 quantity squared plus 1. So it's already in standard form, which is nice. This is x minus h plus k. So that's minus h plus k. So immediately I can pick off what our vertex is. We know this is positive. So based on this specific form, I now know a couple different things. The coefficient out front is 1, so it's positive. We know it's going to open up. And also because it's in standard form, I know that 4, 1 is going to be our vertex. So I can go ahead and plot those points. Here's 4, 1. I know it's going to open upwards, but I do want to find a couple other things as well. We know x equals 4 is our axis of symmetry. So we can go ahead and draw in that dotted line to tell us our graph is symmetric about this. Here's x equals 4. And then you'd also should find your x-intercepts and y-intercepts if they exist. So let's start with the x-intercepts. That would mean that y has to equal 0. So if we try to solve this, we'll go ahead and subtract 1 from both sides. Well, that's going to give us x minus 4 squared is equal to negative 1. If you take a square root and get a plus or minus, you really end up with imaginary numbers over here. So because of that, there's going to be no real x-intercepts. So I'm not going to be able to actually plot them. Now, if we go to do the y-intercepts, all we want to do is plug in x equals 0. So the y value would be 0 minus 4 squared plus 1. Well, negative 4 squared is 16. So it's 16 plus 1. So our y-intercept is going to be at 17. So specifically, that's going to be the point 0, 17. So we'll go ahead and plot that here. Here is our y-intercept. And if you notice, I can immediately tell another point here. Because of our axis of symmetry, that's a distance of 4. If I go 4 more this way to 8, I'm going to have exactly the same y value. So 8, 17 will be another point on our parabola. And now we just need to connect the dots. And here is our graph of f of x. Okay. So the standard form is really useful to make a clean picture of the graph without much effort. So when we want to graph it, we should always put it in standard form. If you have something that's written in general form, so just ax squared plus bx plus c, you've got to first rewrite it by completing the square. So let's go through that process together. Let's graph this function. I don't know the vertex immediately off the top of my head. All I do know is that this is negative x squared, so it is going to open downward. But I need to find that vertex, and I've got to find some other important things. So we want to rewrite this in standard form first. So that means we've got to complete the square. So our first step is we want to group the x terms and factor out whatever coefficient is on the x squared. So we've got our function is negative x squared plus 6x. I want to go ahead and factor out this negative 1 from the x terms only. The 7 will get pushed off to the side. So we take out that negative 1, so it gives us negative times x squared minus 6x, and you leave the 7. Now we want to go through and we want to complete the square on these x terms and balance it out. So whatever I add, I need to make sure I'm balancing and subtracting it from the end. So here's where we're at right now. We need to take this number, divide it by 2, and square it. So we take 6 over 2, square it. It's going to be 3 squared. I'm really adding 9 in here, but not just 9. I'm adding negative times this value. So I'm adding negative 9 which means I've got to add a positive 9 to counterbalance. So this is equal to negative x squared minus 6x plus 9 plus 7 plus 9. Now we can go ahead and factor and simplify this thing. So our function becomes negative times x minus 3 squared plus 16. So now I've got it in that standard form. So our vertex is going to be at 316. Because that value of a is negative, it's going to open down. Then we want to go through and find our intercepts as well before we actually graph this. So the x-intercept, you set this equal to 0. Let's go ahead and add this x minus 3 squared over just to make things positive. So we get x minus 3 squared is 16. If we take a square root, don't forget you get the plus or minus. So we get x minus 3 is plus or minus 4. So the x values of our x-intercept are 3 plus 4 and 3 minus 4. 3 plus 4 is 7. 3 minus 4 is negative 1. So we have two x-intercepts, 7, 0, and negative 1, 0. To find our y-intercept, we just take the function and evaluate it at 0. So that becomes negative 3 squared plus 16. So it's negative 9 plus 16, which is 7. So our y-intercept is 0, 7. So now we go ahead and plot these points. Our vertex is at 3, 16, which is up here. Our y-intercept is at 0, 7. Our x-intercepts are at negative 1, 0, and then also 7, 0. And then our axis of symmetry is at x equals 3, which is right here. And then it opens down, so we connect our dots. And we get our parabola. Okay. So this is our one way to find the vertex of the parabola, but we really have two different ways we could go about it. So the first way is writing it in standard form. If you do have to graph it, this is going to be your best option because it'll tell you everything you need. But if you're just concerned with finding the vertex itself, there's an easier way. So the x-coordinate will be negative b over 2a for that quadratic function. And then the y-coordinate you just find by plugging in that value. So let's go about this second method with this quadratic function. We just want to find the vertex. We don't need anything else. So this one's a lot harder to complete the square because you have that 1/2 out front. So instead we're going to use this formula to help us out. So our x-coordinate of the vertex is h. It's negative b over 2a. So here is our value of b. Here is our value of a. So a is 1/2, b is negative 7. So plugging these into our formula, we find out that it's negative 7 over 2 times 1/2. So it's 7 over 1, or our x-coordinate of the vertex is 7. To find the y-coordinate, I just need the other point this goes through. So the y-coordinate is k. It's our function evaluated at 7. So if you plug that in and simplify everything, you're going to get 1/2 times 49 minus 49 plus 5. Not going to be a pretty number because it is a fraction. So change everything to have a denominator of 2. And you'll find out the y-coordinate is negative 39 over 2. So our vertex is 7, negative 39 over 2. So you can see this be quite a tedious one to actually put into standard form, that utilizing this formula is a little bit simpler. Okay. Now relating this to what we've actually done before, we spent a lot of time solving quadratic equations. Really, when you're finding the x-intercept of a quadratic function, you're setting that function equal to 0. So you end up solving ax squared plus bx plus c equals 0 to find these x-intercepts. Because of that, we can use our knowledge about the discriminant to determine the number of intercepts. So just remember the discriminant is what's underneath that radical, because the x-intercepts would be negative b plus or minus the square root of b squared minus 4ac all over 2a. Based on the value of b squared minus 4ac, we can figure out if we're going to have 2 zeros or 2 x-intercepts. Do we have none? Are they complex? What's going on? So let's look at an example. Let's draw a graph that satisfies the given conditions. So we're told that the value of a for the quadratic function is 0 or less than 0, and then that discriminant b squared minus 4ac is strictly less than 0. Because a is less than 0, we know it's going to open downward, and because the discriminant is negative, so this value under here would be the square root of a negative number, you have no real solutions to this equaling 0. So because of that, you have no x-intercept. So I need a parabola that opens downward and has no x-intercepts. So one possibility, and there's going to be many, many possible options, is you have your vertex here and the parabola opens downward. It cannot come in contact with the x-axis though. So this is one possibility. Another possibility is your vertex could be down here and it opens downwards as well. There's a bunch of different things that would work. Any of them are going to be fine. Okay. Now let's try to go through and let's try to find a quadratic function that has specific instances. So we know the vertex is going to be at -1, -3, and we want it to pass through the point -4, 2. So what we can use is our standard form, because our standard form for a quadratic function is a times x minus h squared plus k. Well, this is our value of h. This is our value of k. So immediately I know a bit about my function. It's going to be a times x minus -1, which is x plus 1, plus k, which is minus 3. The only unknown I have now is this value of a. But I still have a piece of information I haven't used. It's got to pass through the point -4, 2. So when x is -4, the y value should be 2. So we can plug that in. 2 has to equal a times the x value, which is -4, plus 1 squared minus 3. So we just need to go through and solve this. Go ahead and add 3 to both sides. We get 5 is equal to a. -4 plus 1 is going to be -3. So this gives us 5 is equal to 9a. Dividing by 9 gives us the exact value of a in our parabola. So now we know the equation of the parabola is going to be f of x equals 5/9 times x plus 1 squared minus 3. Okay. Now the nice thing about these parabolas is they do have a lot of realistic shapes that occur. So if you think of if you throw a ball to anyone, it goes up, it basically kind of stops going any higher, and then it's going to fall back down. And most of the time that's going to have this parabola shape. So we can model a lot of things based on that. So we're going to look at a specific example where we're told the height of a soccer ball above a ground is given by this specific function. So h of x is -0.0128x squared plus x, where x is going to be the horizontal distance the ball travels in feet. So the first thing we want to figure out is what is the maximum height the ball reaches. Well, this is just a parabola. I know the value of a is negative, so it's got to open downward. So if we look at a picture, it's going to have this kind of shape. The max height is going to occur right here at the vertex. So we need to figure out what is the y value of the vertex to see the maximum height. Well, we can just use our formula since we don't need to put this in standard form. The x-coordinate is -b over 2a. Well, b is +1, a is -0.0128. So if you go through this division, you're going to find the x-coordinate is 39.0625. So this point here is 39.0625. What I want to do is figure out what is this y value. So all we need to do is plug that value back in. So you get -0.0128 times x squared plus x itself. So if you go through this, you're going to find out the y-coordinate of the vertex is 19.53125. So the max height the ball is going to reach is 19.53125 feet. So now let's go ahead and let's figure out what is the horizontal distance the ball travels. So if you think about this function, both of them have an x in it, so you can factor that out. So what we actually want to do is we want to see, when does the ball start on the ground, when does the ball end on the ground. So I need to figure out what those x-intercepts are equal to. So I need my function to equal 0. So since it's nice and factored, that tells us immediately x is equal to 0, or negative 0.0128x plus 1 is equal to 0. If you solve this by subtracting 1 and then dividing by negative 0.128, you'll find out x is going to be 78.125. So this coordinate here would be 78.125. This is our vertex coordinate. Your ball is going to start at 0, 0. It goes up to that height, and then it comes back down to the ground. So you kick the ball up, and it falls back down. So the distance it actually travels is the difference between these 2 points. So it'll travel 78.125 feet. So you can see a lot of different stuff, a lot of different applications. Projectiles are going to be the main one that have this shape though.